All right, welcome back to the deep dive. Today we're diving into the world of CPU scheduling. You know, that thing that makes sure your computer doesn't just completely freeze up when you have like a million tabs open.
Yeah.
It's kind of like air traffic control, but for all the processes fighting for your computer's attention.
Yeah, it's pretty fascinating stuff. We've been poring over some dense lecture notes on operating systems to get a grip on this.
Really trying to understand the nitty-gritty of it all.
Absolutely. So we're going to break down how exactly your computer prioritizes all the different tasks it has to do, and hopefully shed light on some of the clever tricks it uses to, keep everything running smoothly.
So starting from the top, multi-programming is really at the heart of this whole thing, right?
Yeah, that's the foundation. The idea is to keep the CPU, the brains of the operation, as busy as possible by having multiple programs loaded and ready to roll.
So it's not just sitting idle waiting for one thing to finish before moving on to the next.
Exactly. And to make this whole juggling act work, programs go through these cycles of using the CPU for a bit, which we call the CPU burst.
Okay.
And then they might need to wait for something, like data from the hard drive or the network. That's an I/O burst, and the scheduler has to kind of manage this whole dance of CPU bursts and I/O bursts.
Got you. So it's constantly switching back and forth between different tasks.
Right.
And the CPU scheduler is the one calling the shots.
Precisely. It looks at what we call the ready queue, which you can kind of think of as like a line of programs all waiting their turn to use the CPU.
Okay.
And it picks the next one in line. This happens whenever a program finishes its little bit of work or if it needs to wait for something else.
You know, sometimes the OS can just step in and say, all right, time's up next.
That's a brain.
Preemptive scheduling, right?
Yeah, exactly. It basically allows the operating system to interrupt a running program and switch to another one.
I see.
Now, with non-preemptive scheduling, the program gets to run until it finishes its CPU burst on its own terms. But with preemptive, it can get kicked off even if it's not quite done.
Got it. So then the dispatcher is like the actual bouncer that makes the switch happen.
Yeah, that's a good analogy. And the whole process of switching from one program to the next, saving the old program's state and loading the new one, is called context switching.
Context switching, right. So with all these different ways of scheduling, what are we actually trying to achieve here? What makes a good scheduler? What are we optimizing for?
Well, the big picture is we want the CPU to be as busy as possible, right?
Right.
High CPU utilization, squeezing every last drop of processing power out of it.
Makes sense.
And we also want to get as many tasks done as possible in a given amount of time. That's throughput.
So efficiency is key.
Absolutely. But we also want to minimize the time each individual task takes to finish its turnaround time.
Okay, yeah.
And the time it spends just sitting there waiting, it's waiting time.
Right.
And especially for programs that interact with the user, like, your web browser or a game, we want to minimize that lag between you clicking something and something actually happening on the screen.
Yeah.
That's response time.
Yeah, responsiveness is super important for a good user experience. So let's get into the actual strategies now, starting with first come, first served, or FCFS. That sounds pretty self-explanatory.
Yeah, it is. Basically, whichever process requests the CPU first gets it first. No special treatment.
Simple enough.
But, imagine if a super long task comes along at the very beginning. All the shorter tasks behind it are stuck waiting, leading to what we call the convoy effect.
Oh, I see, like a bunch of cars stuck behind a slow truck.
Yeah, exactly. And that can lead to longer average waiting times for everyone.
Right. So even though it sounds fair, it might not be the most efficient in practice.
Right.
Okay, so what about shortest job first, or SJF? That sounds like it might be better.
Yeah, the idea behind SJF is to always pick the task with the shortest next CPU burst. So we're trying to, get those quick wins out of the way first.
Okay.
In theory, this actually minimizes the average waiting time for all the processes, but the tricky part is knowing how long those CPU bursts are going to be in advance.
Yeah, it's like trying to predict the future.
Exactly. Now, there's also a preemptive version of this called shortest remaining time first, SRTF, where we can actually interrupt a longer task if a shorter one comes along.
Ah, okay, so even more dynamic.
Right.
So are there times when we actually assign priorities to tasks?
Yeah, that's priority scheduling. Each process gets a priority level, and higher priority processes get to go first. You can actually think of SJF as a kind of priority scheduling where the priority is based on the predicted burst length.
Oh, I see.
But one issue with priority scheduling is the risk of starvation.
Starvation.
Yeah, where a low priority process might end up waiting forever if there are always higher priority tasks coming in. One way to deal with this is something called aging. where the priority of a waiting process gradually increases over time.
So it eventually gets its chance.
Exactly.
What about round robin? That sounds kind of like taking turns.
Yeah, exactly. With round robin, we give each process a fixed time slice to use the CPU called a quantum.
Okay.
And if it doesn't finish within that time, it gets sent to the back of the line and has to wait its turn again.
So everyone gets a fair shot.
Yeah, and it's especially good for interactive systems because it makes sure things feel responsive,
Right.
but it can sometimes increase the overall turnaround time compared to something like SJF, and choosing the right size for the quantum is really crucial.
So it's like sharing a single-lane highway.
Hmm.
Everyone gets to move forward a little bit, but it might take a little longer overall.
Yeah, that's a good analogy.
Now, what about more complex setups like multi-level queues?
Multi-level queues divide the ready queue into separate queues, each with their own scheduling algorithm.
So like different lanes for different types of traffic?
Right, so you might have one queue for interactive processes that uses round robin to keep things responsive, and then another queue for background processes that uses XCFS.
Okay.
And then on top of that, you need a way to schedule between those queues, like giving one queue higher priority than another.
Got it. So even more levels of complexity.
Right. And then we have multi-level feedback queues, which take things even further.
Oh boy, more levels.
Yeah, but this is where it gets really interesting. With a multi-level feedback queue, processes can actually move between the different queues based on their behavior. So if a process keeps using its entire time slice, it might get demoted to a lower priority queue.
So the system learns and adapts based on how the processes are actually behaving.
Exactly.
Okay, with all these different algorithms, how do we even know which one's the best? How do we measure their performance?
Well, there are a few different ways to evaluate scheduling algorithms.
Oh,
One is deterministic modeling, where we use a specific set of tasks and run simulations to see how each algorithm performs. Then there's queuing models, which use mathematical formulas to estimate performance based on things like the average arrival rate of new processes and the average CPU burst times.
so trying to predict how the system will behave overall.
Right. Then there are simulations, where we create a software model of the entire system and run experiments with different schedulers.
Okay.
And finally, the most accurate but also the most challenging method is to actually implement the schedulers in a real operating system and see how they perform in the wild.
So kind of like a real-world test drive.
Exactly.
So it sounds like there's no one-size-fits-all answer when it comes to CPU scheduling.
Definitely not. It really depends on the specific goals of the system and the types of processes that are running. It's a constant balancing act between efficiency and fairness.
Well, this has been a really insightful look into the world of CPU scheduling. It's amazing to think about all the complexity that's going on behind the scenes to keep our computers running smoothly. It makes you think about how we schedule our own tasks in our daily lives. Are there any strategies from CPU scheduling that we could apply to, like our to-do lists? That's something to think about. Thanks for joining us on the Deep Dive.
My pleasure.